Okay, let's take a step forward on the emissions that we talked about. We talked about GDP, emissions, population, and so on, and it turns out that they are related in some ways with an identity that we'll look at. So before that, let's just touch on the population projections as well. I mentioned that the fertility rates have dropped and the annual rate of increase of population has been dropping, as we saw here. So even China and India are reporting maybe dropping to replacement rates of fertility, which means 2.1 children per person, including deaths. You want more than 2 per person for population to remain steady or grow. So here we are looking at world population projections, ILIASA probabilistic projections compared to UN projections, which already tells you that there are multiple projections. So UN high variant population projection by 2050 is 10.5 billion with the a large range of 95% uncertainty here, and UN low variant here is at 8 billion by 2050. And UN medium variant is at 9.1, and the ILIASA projection based on 2006 population goes here, and by 2100 it ends up at 8.4 billion, and the range here is quite large, from 6.2 to 11.1, or on the upper end here at almost 13 billion. By 2100 there is a 80% chance the global population will number between 6.2 and 11.1 billion if you take a certain range of 80% probability. So with all probability, continued education of women, women's rights, financial independence is going to keep dropping the population, and there are even books called Empty Planet which project that there may be a population collapse and we might end up with maybe 1 billion by 2100 instead of 6.1 to 11.1 or whatever. Keep that in mind as we go forward here. What determines total CO2 emissions? The KI identity breaks down the total emissions into key elements driving these emissions. So total CO2 emissions do depend on the total population because of per capita consumption times CO2 per person, and then total CO2 emissions will of course depend on the total population and the total CO2 emissions. But here CO2 emissions per person depend on income, so goods and services per person measured in dollars, so that will be GDP per population, times technology, which is a measure of energy intensity of lifestyles. So that can be split into energy intensity or energy consumed per dollar of the income, and carbon intensity or CO2 emitted per unit of energy consumed. So then it amounts to energy per GDP unit times CO2 per energy unit. So this gives you energy intensity. So we can improve energy intensity by increasing energy efficiency or switching to less intensive industries. So it begins to tell you how to handle total CO2 emissions in this way. So carbon intensity means switching to renewable energy, switching to nuclear, substituting gas for coal. So this is a partial solution, capturing and storing fossil fuel CO2. So this is another way to look at it, but in general you can say the principle is that you want to decrease the energy intensity of your GDP and the carbon intensity of your energy. Those are kind of the big line items that you can aim for. So if you look at KI identity drivers of CO2 emissions, here are the CO2 emissions that have gone more than 250% or so since the 1960s, when Charles Keeling started measuring things. GDP per capita has gone up by more than 150% for the world. The distribution is very uneven, so you have to be careful. Population total has increased, but as we said, the rate of increase has flattened out. Good news is that the carbon intensity, or CO2 emitted per unit of energy, has shown a drop but has flattened out, which is not good. Energy intensity, so energy used per unit of GDP, has dropped, and this again is an uneven distribution, with some countries doing much better than others, and it can also hide the fact that you went from something like coal to natural gas, which is emitting less, but it's still not good for the overall emissions. Okay, and carbon intensity of CO2 per dollar has also dropped. Is this good enough? Of course not, because when we look at the total emissions, they have continued to increase. So this is what gives us the warning message about how far we can go emitting carbon before we hit the 1.5 degrees C or 2 degrees C warming targets. Just to get a good sense, energy intensity is measured as primary energy consumption per unit of gross domestic product. This is measured in kilowatt hours per 2011 dollars. So that's the parity purchasing power. And you can see that some countries like Canada, Russia, China, they have high energy intensities, and other countries, typically poorer countries, have lower energy intensity. But good news is that some rich countries in Europe, in the US, also have relatively low energy intensity, which means they are doing something better than the other first world countries like Canada. And of course, Middle East continues to be very energy intensive, considering they are selling a lot of fossil fuels to the rest of the world. And there are some hotspots here. This could be Libya, maybe. I hope I'm right. Egypt, Libya, maybe. Yeah. So there is one hotspot here as well in East Africa. So what we can do is then take these and compare the energy flows between 2018 and 2050. So we are looking at primary energy supply from oil, coal, natural gas, biomass, solar thermal, geothermal, solar PV, hydro power, nuclear, and wind. And we are looking at transformation for the user, and you can see that the final energy demand from transport, from manufacturing, from buildings, from energy sector, and other together is about 2.7 petawatt hours per year, and this is going into road, maritime, aviation, rail, that's the transportation split, manufactured goods, base materials, iron and steel, feedstock, so this is for biofuel energy productions, space heating, water heating, cooking, appliances, lighting, and space cooking. Okay, so how does it compare? What do we expect in 2050? These are projections. So good news that energy would drop in the final use. The primary generation here from the combination of natural gas, coal will hopefully drop off as well. Biomass, geothermal, solar PV, hydropower, they are all larger compared to the width of the bands here, for example. And what is being consumed in cooking and so on, so hydro, biofuel, solar PV, solar thermal, and nuclear, wind should go up. So you can see now the splits again compared to what is being consumed on the road and maritime and aviation now versus by 2050. So these are projections, and the total demand electricity generation, sorry, I cannot read it here, it's down to 60 petawatt, up to 60 petawatt hours per year. So we have not only changed the distribution of primary energy supply, but also we have increased the total energy generation, electricity generation. So we need to meet the increasing demand without increasing emissions. So obviously there is a big demand for weeding out the fossil fuels, especially the most emitting ones like coal. For example, natural gas is much better, oil is heavier, and so on and so forth. So keep these things in mind. But the good news is that the share of land required to generate all the energy from solar is basically available. So the space demand is not very high. In these red regions it's 0.1% or less. In these bluish colors it's below 1%, and in the grayish colors it's below 5%. So as you go to higher latitudes, obviously seasonality of the number of sunny days changes, so you increase the area needed as opposed to the global south and the tropics, for example. And monsoons, for example, make a difference in a country like India or these South Asian countries. Renewable energy generation has gone up tremendously. So you can see hydropower, which is renewable, has gone up. Wind, solar, and other renewables together have gone up from about 1,000 terawatts in 1965 to more than 7,000 terawatt hours by 2020. And the projections are that these will continue. Of course, the question is how much, what fraction of the total energy demand is this? What fraction of the total energy generation is this? Even the most progressive countries like Germany, for example, or Sweden, Norway, Denmark, and so on, some of them have very high percentage of energy from renewables. But as I said before, Germany is still digging for coal, so it is still burning fossil fuels, not just fossil fuels but coal. So let's just focus on the good news then. Share of primary energy from renewable sources is here. You can see that some countries are doing well, up to 85%, and they typically tend to be here. Brazil is doing well because it's burning a lot of biofuels, sugarcane, and so on, but there are other issues that we talked about before in terms of deforestation and so on. Canada is doing better, even though its energy intensity is high. It's somewhat better than the US, for example, in its share of primary renewable energy. China is better than India. Pakistan is appearing slightly better than India on this map, but India is growing very fast in solar and renewables as well. And biofuel energy production has gone up. United States dropped off recently. Brazil has dropped off. Germany, UK, Mexico. But we talked about the problems of biofuel and unintended consequences on deforestation, pesticides, and water quality problems, air quality problems, and so on. Food security issues, water security issues. Other good news is that we are also increasing number of cars, but still the market share is fairly small compared to the internal combustion engines. And there are many other exciting inventions happening that we will come back and look at in the next podcast. Okay.